Well, you know what I'm going to do? I'm going to...
Recording in progress.
Okay, I'm going to record everything, and I can send a link to the recording. So maybe why don't we get started? And then as they come in, we can talk about the problems. Do you have questions on the homework? And I work them on the board, so. You want to go through one of them? Okay. Let's see. Let's look at problem number 3. Let's look at that one then. Is that okay? Okay. I don't know if it's if it's too small for you, my display. Oops. It might be kind of small, but okay. Oh, you need a password. I don't have a. I didn't add a password to this. Yeah, I didn't add a password to this meeting, so I'm surprised. Okay. All right, so let's look at number 3. So number 3, we have a cyclical heat engine. And get 25 kilojoules of heat transfer to the environment. I'm just using my numbers. And for every 95 kilojoules that goes into the engine. And he wants to know the efficiency. So what did the problem give us first? I guess that's the question. What kind of information have we been given? I'm trying to find a better marker. What information has been given to us in problem 3? In other words, when it says 25 kilojoules of heat transfer to the environment, what does that represent? The heat that's leaving the engine. So this is Q sub C, right? And then this is the heat going into the engine. What do we call that one? Okay. Well, this is the heat that's added. So this, I'll just say this is Q hot. And so the efficiency is the work that the engine does divided by Q hot. Which is also, the work done by the engine is Q hot minus whatever is expelled over Q hot. So Q hot minus Q cold is the work done. So you put in this much energy, you put in this heat, this much work is done, this is what's given off. Okay. And so then we take Q hot, which was 95 kilojoules, minus Q cold, divided by Q hot. And this comes out to 0.737, but it wants a percentage. So you take 0.737 times 100. That's it. Okay? So the next question is, how much work does it produce when you put in 700 kilojoules of heat? So it says, if Q hot is 700 kilojoules, and again, I'm using my numbers, you're going to have different numbers, right? If I put in 700 kilojoules, what is W? Well, I know my efficiency. I know Q hot. I can solve for this. Okay. I'll use the letter E for efficiency. I'll do the algebra. So I take 0.737 times 700. And this comes out to 516 kilojoules. Is that okay? Okay. Another one you want to look at, or do you have questions in general on this topic? Amir or Jacqueline, do you have questions? Either on the homework or the topic that you've been discussing in class?
Yeah, actually, I have not started this one yet.
Okay.
But if you choose, can you do another one? Or
Choose another one?
Yes,
Okay.
a little harder one. Thank you very much.
Let me try number 10 then. Okay. Number 10, and I'll be honest, number 10 is strange just because they use an approximate expression for entropy change. I think he said you guys talked about it in class. So let me change something here. And again, I don't know if you can see that very well on the screen. Okay. So let's try number 10. Actually, I'll start here. So in reaching equilibrium, how much heat transfer occurs from 1 kilogram of water? So I have 1 kilogram of water. And again, I'm using my values. And it's placed in contact with another kilogram of water. And you want to find the energy transferred. Okay. You want to see how much energy is transferred between these two. One's going to lose energy, the other one's going to gain energy. But in order for me to figure this out, I need to know the final temperature. So what's the final temperature? And I can do it the long way. I can set it up as a calorimetry problem. And this problem is actually not that hard because the masses are the same. But let me set it up as a calorimetry problem. Okay? So I'm going to say that the sum of the Q's equals 0. And I'm going to say that this isn't the hot one. This is the cold one. Okay? Although they're the same mass, but I'm going to say M hot, C, which is the specific heat of the water, times T final minus 39.0 plus M cold times C, T final minus 18.5 equals 0. Since this mass and this mass is the same, and since the C's are the same, then I can just cancel these two out, and I can say T final minus 39.0 plus T final minus 18.5 equals 0. 2T final equals, if I move these, let me do it. Let me do it this way. 39 plus 18.5 2T final. I'm sorry if I'm not using the units here. That's my T final in my problem, okay? I want to figure out how much energy is gained or lost by either one. And we know that whatever this thing loses is going to be whatever this gains. So I only have to do the calculation once. So let's do this one. The heat gained, or the energy gained by the cold water is going to be this. So you have 1 kilogram. And, okay, so I need to mention this. When I look up the specific heat of water, I get 4184. But in WebAssign, for this particular problem, they use 4186. Okay, so make a little bit of a difference. But in their solution, they use this value. And again, I don't have enough space to write all the units here, so I apologize. And then I do T final minus T initial. And so the energy transferred is that much during the process. Okay, so that's part A. Part B says, what is the change in entropy due to this heat transfer? So you want the total change in entropy. And so this is, it's unusual the way they state this, but that's fine. I mean, because you can't write change in entropy just Q over T because the T changes during the process. And so they say that delta S is Q over T average for the process. Okay? So I need to figure out delta S for the cold. And I got to find delta S for the hot. Okay, in either case, this is the amount of energy. One gains this, the other one loses this. Okay, so let's find delta S cold. It's going to be 42,900 divided by the average temperature. So, and I got to be careful, the temperature in the denominator is in Kelvin, right? Okay, so this has to be in Kelvin, but first let's find the average temperature. It's going to be this value plus the 18.5 divided by 2, and then I got to add 273. So it's 28.75 plus 18.5 divided by 2 plus 273. And when I do that, I wrote it down, I get 292. Okay. Let me double check. I'm sorry, not 292, 296.63. Okay. And then when I do the other one, delta S hot, that's going to be, but this is going to be negative because the hot one lost energy, right? The cold one gained this energy. The hot one lost that energy. But then the average temperature, let me erase this. T average hot is going to be 39 plus 28.75 over 2 plus 273. And that comes out to be, if I can find my 306.75. So the total change in entropy, let me know if you can't see down there, okay? So you take this number and this number, you take this positive number and add it to this negative number, and you get 4.83 joules per Kelvin. And then the last part, all you do is you take how much work is made unavailable. You take the low temperature and multiply by delta S. So for part C, you just take T low times delta S. And T low is in my case, is the 18.5 degrees. Okay? Is that okay? Is that clear enough? Okay. Number 11 has that same issue where you got to take the average temperature to find the change in entropy. So you folks have an exam on Thursday? Okay. It's going to be all on thermodynamics, right? You're going to go through the cycle, and do you have questions about going through the cycle or anything? No questions? Okay. And you folks have done all your labs already? I mean, all your labs are done. You're okay. So yeah, I'm just, whatever question you may have, all your labs are finished. Okay, cool. Let me do one more problem then. I'll look at number 7. Okay, it's not a long one, but so number 7 says, suppose you have an ideal refrigerator. So you have an ideal refrigerator. And my value is minus 13 Celsius. And it transfers heat to another environment, 56. So this is Q cold. I mean, this is the cold end. And then the hot end and then what's the coefficient of performance? So I guess the question is, what is the coefficient of performance What is the coefficient of performance for a refrigerator? Well, it's going to be Q cold over W. But if for an ideal case, it's going to be T cold over T hot minus T cold. And of course they have to be in Kelvin. So what's T cold here? I got to take this and convert to Kelvin. I'm dropping a 0.15 every time, but and then the denominator T hot is 56. And when you do this work, you get 3.77. Generally, a lot of the homework problems are easier. The last two are the ones that are harder. Okay. The other ones are pretty straightforward. Okay. I guess if you don't have any more questions, I guess I'll end it here. And what I'll do is, I've recorded this, so I'll give you guys, I'll give everybody an email as to where it's at. Okay, then you can look at it. Okay? So no other questions? All right, so good luck on Thursday. All right, see you. No problem.